Hello again. Welcome to another lesson in geometry. Today we are covering section 10-4, perimeters and areas of similar figures. So what does it mean when two figures are similar? So remember, similar figures have the same shape, but not necessarily the same size. So their sides are proportional, and angles are congruent. Okay? So two squares are always going to be similar because they have proportional sides, okay? And then all the angles are going to be 90 in both of them, so they would be congruent angles. So are corresponding angles of similar figures always congruent? And this should be yes. Are the corresponding sides of similar figures always proportional? And this should also be yes. So sides are not congruent, sides are proportional. Okay, angles, however, are congruent. So circle the pairs of similar figures. So this is a right triangles, and they both have the same number for the legs. So that means they're 45, 45, 90 triangles. So they're going to be congruent for all the angles. And the sides are proportional because each one's going to be in the ratio of 3 to 2 or 2 to 3. So this is yes. This one's definitely no. The sides are not proportional even though the angles are congruent. And this one's going to be yes. They're both regular pentagons. Okay, so all their angles are going to be congruent and the sides are all proportional. They're going to be like 8 to 6 or 6 to 8. Okay, all right. Vocabulary builder here. We have radius. So some related words is apothem. Remember, that's kind of like the radii. It's like the, well, similar to the radius, but for a polygon, although we have radii also on a polygon. And we have center, okay? And then the definition, the radius of a regular polygon is the distance from the center to the vertex. So remember the apothem was, we take our old square again, the distance from the center to perpendicular to one of the sides, and our radius is going to be the distance from the center to one of the vertexes. Now we used the radii last time, but we never wrote down a definition for it. All right, so our main idea here is the radii of a regular polygon divide the polygons into congruent triangles. So if we put in all of the radii, we get congruent triangles. So each one of these triangles is congruent to the other ones. Okay. All right, cross out the segment that is not a radius of the regular pentagon A, B, C, D, E. Okay. So let's see. OA, that's definitely a radius. OD is definitely a radius. It goes from the center to one of the vertices. OB is a radius. It goes from the center to a vertice. OE is a radius. It goes from the center to a vertice. OC is a radius. It goes from the center to a vertice. But OF is not a radius. It goes from the center to a place halfway between the vertices. So that's an apothem. And that means that this is the one that's not good. So we'll cross them out. Okay. All right, so the radii of a regular pentagon are always going to be congruent. Okay, otherwise we wouldn't have congruent triangles formed from them. And the triangles formed by the radii and the sides of the regular pentagon ABCD are also congruent. So we do that above. The radii of a regular polygon divides the polygon into congruent triangles. All right, let's flip it over and check the second page. First one here on the second page says theorem 10-7, perimeters and areas of similar figures. And this is what we're working with today. So if the scale factor of two similar figures is A to B, then the ratio of their perimeters is also going to be A to B. However, the ratio of the areas will be A squared to B squared. So let me show you what this is talking about. Let's go back to our default square here. It's easy to see similar figures for them. So here's a square that has sides of 2, 2, 2, and 2. And that's definitely going to be similar to a square that has sides 5, 5, 5, and 5. Okay? So the ratio of one of the sides is the new one to the old one, 5 to 2, which is 2.5. So let's check their perimeters. The new perimeter is 20. The old perimeter was 8, and if you reduce that, you also get 2.5. And that's why the perimeter ratio is the same as the side ratio, the scale factor of the two figures. Okay. All right, so the ratio of their areas, though, is going to be a squared to b squared. So let's see what that's talking about. So this guy has an area of 25. This one has an area of 4. So that's 25 over 4. So you can see from the fraction, this is 2 squared and 5 squared. So it works out perfectly. And if we were to work that out, then 25 over 4 would be, let's see, well, let's get a calculator out. 25 divided by 4 is 6.25. And if you were to square 2.5, you would also get 6.25, okay? And that's because it's in the ratio of the squares, all right? So it's going to be important as we go on. When we start to study volume, we'll find out that the volumes are in the ratio of a cubed to b cubed for two similar shapes that are volumes, okay? So the name of the ratio of the length of one side of the figure to the length of the corresponding side of the figure is the scale factor. That's this one. One side to the other corresponding side gives me a scale factor of 2.5. The big square is 2.5 times bigger than the small square. So if the scale factor of two figures is 1 to 2, then the ratio of their perimeters would also be 1 to 2. If the scale factor of two figures is 3 to x, the ratio of their perimeters would also be 3 to x. And the way you could think about it is a side or a perimeter, that's still just a length, okay? So when you're measuring length, it has the same scale factor. But if you compare length measurements with area measurements, the scale factor has to be squared, okay? So if the scale factor of two figures is 3 to 5, then the area is going to be 3 squared to 5 squared. If the scale factor of the area of two figures is 1 to x, then its area would be 1 squared to x squared. All right, problem number 1 down below. Finding the ratios in similar figures. So this is two similar polygons have corresponding sides in the ratio of 5 to 7. What is the ratio of the larger to the smaller for their perimeters? What is the ratio of the larger to the smaller of their areas? So first off, we need to circle the polygons that have the ratio of 5 to 7. Okay, this is a 1 to 2 ratio, or a 2 to 1, but certainly not 5 to 7. This is a 14 to 8, which will reduce to 7 to 4, or 4 to 7. So this guy is not 5 to 7. And this is a 14 to 10, which is a 7 to 5, or 5 to 7. So this is the ratio of 5 to 7, okay? In similar figures, the ratio of the areas equals the ratio of the corresponding sides, or the ratio of the perimeters. This should be perimeters. Remember, perimeters have the same ratio as the sides. In similar figures, the ratio of the areas or perimeters equals the ratio of the squares. Squares is going to be area. And this makes sense because perimeter is a distance and area is how many squares fit inside it. All right, so let's complete this. The ratio of the larger to the smaller is 7 to 5. Okay. So this guy is larger to the smaller. That's 7 to 5. We were given the ratio of 5 to 7, smaller to larger originally, okay? And the ratio of the larger to the smaller for the perimeters is going to be exactly the same, 7 to 5. And the ratio of the areas is going to be 7 squared to 5 squared, which is 49 over 25, okay? And that 49 over 25 will not reduce because if a 7/5 doesn't reduce, then squaring it is not going to make it reduce either. All right, let's flip it over and check out page 3. Okay, on the top of the third page, we have problem number 2, finding areas using similar figures. So the scale factor of two similar polygons is 3 to 4. So that means if we compare one of the sides of the smaller polygon to the side of the bigger polygon, we get 3 to 4 ratio. So the area of the larger parallelogram is 96 inches squared. So this one over here, whatever kind of polygon it is, has an area of 96 inches squared. 96 squared. Okay, so 96 inches squared. And then this one over here, we don't know. So it's x inches squared. Okay, what is the area of the smaller polygon? So write true or false for each statement. So the ratio of the areas is 3 to 4. This is false. So remember, the ratio of the areas is the square of the ratio of the sides. So the ratio of the areas is 9 to 16 is true because 3 squared will give us 9 and 4 squared will give us 16. So use the justifications below to find the area A of the smaller polygon. So we know that the area of the ratio of the area will be 9 to 16. And we don't know the smaller area, but we know the bigger one. So we just wrote a proportion here. Okay, we're going to do our cross products. So 16 times A will equal 96 times 9. Okay, and then we're going to go ahead and multiply 96 times 9, and that will make 864. And then we're going to divide both sides by 16. Okay, and 864 divided by 16 will give me 54. So the area of the smaller polygon is going to be 54 inches squared. Okay, so this is really, A was what they were using, so this will be 54 inches squared. All right, problem number 3, applying area ratios. So the scale factor of the dimensions of 2 smaller pieces of window glass is 3 to 5. Okay, the smaller piece costs $2.50. How much should the larger piece cost? So the scale factor of the dimensions, so that's the sides of it, is 3 to 5. So the smaller glass is 3 on one side and the bigger one is 5 on that corresponding side. The smaller piece costs $2.50. The larger piece, we want to know what will this cost. Okay, so use the information in the problem to complete the reasoning model. So when you buy a piece of glass, it's not by how long it is on one side, it's the area that you're paying for. So we need to find out the ratio of the areas. So the ratio of the areas is going to be 3 squared to 5 squared, which is 9 to 25. So then we can set up a proportion to solve for the cost of the bigger piece. So the smaller piece ratio is 9 when the bigger is 25, so 9 to 25. The smaller piece costs $2.50, and we don't know the cost of the bigger piece, so we put C there. Okay. Then we're going to do our cross products. So this will be 9C equals 250 times 25. And then we're going to get 9C, and we'll just do multiplying. So 25 times 250 will give us 6250. And then we're going to divide both sides by 9. So 6250 divided by 9 is about 694. So that would be the cost of the bigger glass. So the large piece of glass should cost about $6.94 if the cost is in proportion. Okay, on our last page we have problem 4, and this is going to be going in reverse. So we're going to find the perimeter ratio when we know the areas. So the areas of 2 similar rectangles are 1875 feet squared and 135 feet squared. So we have 2 rectangles. We have a small one and a big one. And the area over here is 1875 and the area over here is 135. But we know that their sides are in proportion. Okay, so what is the ratio of their perimeters? We don't actually have to find the perimeter, we just need to find the ratio. All right, so down below we have the work to do that, okay, and we have to put in the justifications. So the first thing they said was area squared over b squared, a squared over b squared equals 135 over 1875. And this is a proportion, so write a proportion. So that's using that one. Proportion. And where did this proportion come from? All right, so we know that area is going to be the ratio of the area is the ratio of the sides squared. So they just decided still that side A and this corresponding side B. And we knew that if we squared A, okay, and we squared B, that should be the ratio of their areas of the 2 similar figures, and we already knew the areas of the 2 similar figures. So we put the A1 with 135 and the B1 with 1875. Okay. All right, so then they reduced the fraction that's on the left there. So 135 over 1875 reduces to 9 over 125. Okay, so they simplify the fraction. So that takes out a simplify. All right, and then let's see, what did they do on the next step? They took the positive square root on each side. So they did the square root over here and the square root over here. And that gave me A over B, and on the other side we get 5 root 5 on the bottom and 3 on the top. So this is take positive square root. okay, on each side. All right. And then we had to rationalize the denominator to get that square root off the bottom. So that's what they're doing here. They're multiplying both the bottom and the top by root 5. So rationalize the denominator. Okay. And the last step here, they just simplified that rationalization. So this is a simplify. So now we know the ratio of the sides. The ratio of the sides is 3 root 5 to 25. All right? So this is the ratio of the perimeter, which is also the ratio of the sides. Because remember, perimeter and side will have the same ratio. All right? So we have a lesson check here. As always, pause the video, try the lesson check yourself, which is another going backwards problem, and then come back and see how you did on it. Okay. All right, welcome back. So our lesson check says the area of one rectangle is twice the area of another rectangle. So once again, we have two rectangles. We don't know their actual dimensions, but we know the area over here is going to be twice as big as the small area. So it could be something like this, 10 and 5, or 150, or 250 and 125. So something like that. All right, so this area we don't know, but compared to that one should be twice as big. Okay. All right, let x and y be the sides of the smaller rectangle. So we'll let this be x and y. Complete the area of the smaller rectangle. So the area of the smaller rectangle is xy. The area of the larger rectangle then, so let's try this picture again. So the smaller rectangle is x by y, so its area is xy. The bigger rectangle is supposed to have twice as big an area, so that'd just be 2 times xy. We don't know its dimensions, okay, but we know it's twice as big. So the ratio of the larger to smaller areas is going to be 2xy for the larger, 2xy for the smaller. But I'm going to go ahead and reduce that ratio because we have xy in both, and we know neither one can be 1 or 0, so we don't have a rectangle. So this is really this fraction, and that will just reduce to 2 over 1. And that will help us out in the next step. All right, so find the square root of the ratio of the larger to the smaller areas to find the scale factor. All right, so we got to do the square root of 2 over 1, which is the square root of 2 over the square root of 1, but the square root of 1 is just 1, so dividing by 1 doesn't change. So this ratio is the square root of 2 to 1, because we have to keep a bottom for a ratio, because the scale factor in this case is root 2 to 1. So the perimeters have the same ratio as the scale factors. Remember, the areas have the ratio of the scale factors squared. All right, so check off the vocabulary for what you understand here. We have similar polygons. We've been working on those for quite a while. We have the radius of a polygon, which remember now, for a regular polygon, the radius is from the center to a vertice. Same with any polygon, whether it's regular or not. And then we have perimeter, distance around the shape. And we have area, how many squares fit inside the shape. So rate how well you can find the perimeters and areas of similar polygons. You should be in here. You can find those perimeters and areas. Remember, given a ratio of 1, we can find the ratio of the other. That's the new stuff for today. All right, I'll see you in class next time.